Tonight, we're going to try to count the stars. Not in the way that children mean when they lie on their backs in a field and attempt to count what they can see overhead, but in the way that science means, starting from direct measurements of nearby stars, building a systematic picture of how stars are distributed by type and brightness, extending that picture across the Milky Way through observations that penetrate the obscuring dust of the galactic plane, then scaling outward through the 2 trillion galaxies of the observable universe. Using the light those galaxies collectively emit, and arriving at a number that represents the best estimate of how many hydrogen-fusing stars currently exist in the portion of the cosmos we can in principle observe. The answer, to give it immediately so the rest of the night can be spent understanding what it actually means, is somewhere between 100 sextillion and 1 sextillion times 1,000. In scientific notation, the range is roughly 10 to the 23rd to 10 to the 24th. The commonly cited figure, the one that appears most often in astronomy textbooks and popular science writing, is in the neighborhood of 200 sextillion, about 2 times 10 to the 23rd. To give this number some useful context, there are estimated to be roughly 10 to the 19th grains of sand on all of Earth's beaches and deserts combined. The number of stars in the observable universe exceeds the number of grains of sand on Earth by a factor of roughly 10,000. Knowing the number is one thing. Understanding the specific intellectual history of how that number was assembled, what each component of the estimate rests on, where the largest uncertainties are, and why some portions of the estimate remain genuinely controversial more than a century after astronomers first attempted a serious census, is what transforms an impressive fact into genuine understanding of what the universe contains and how we know it. The specific sources of uncertainty that span a factor of several in the total count are not merely gaps in data waiting to be filled by a better telescope. Several of them are genuine physical problems. We cannot see the full extent of many galaxies because they are too distant to resolve into individual stars. The mass function that describes how many low-mass stars exist per high-mass star is not certainly the same in every galaxy. Dust obscures large fractions of many galaxies including our own, and the question of whether the universe is finite or infinite, and whether there is more universe beyond what we can observe, adds a layer of philosophical complexity to even defining what we mean by the number we are trying to count. By the end of tonight, you will understand not just what the best estimate is but precisely why it carries the uncertainty it does, which observational and theoretical tools were used to build it, where those tools are most and least reliable, and what would need to happen for the estimate to change significantly in either direction. You will also understand what the number says about the universe's richness, its history of star formation, and the statistical context it provides for the question of life elsewhere in the cosmos. If this kind of complete, honest, and technically grounded tour of one of astronomy's great questions is what you come here for, subscribe and leave a like. This channel exists to give you the real answers, not just the impressive headline numbers. Now, let us begin with why the number matters even before we start counting. Tonight's exploration of the stellar census is also an exercise in understanding how science produces reliable estimates of quantities that are far too large to measure directly. The process involves direct measurement of nearby objects, theoretical models that extend those measurements to objects too distant or too faint to measure individually, and cross-checks between different approaches that test whether the various pieces of the estimate are mutually consistent. When they are consistent, confidence in the estimate grows. When they are not, the discrepancies themselves become important scientific signals pointing towards something that is not yet understood. The specific cross-checks available for the stellar census are both numerous and imperfect. The total stellar mass derived from galaxy luminosity should be consistent with the total baryonic mass derived from cosmological measurements. The star formation history integrated over cosmic time should produce approximately the current stellar mass. The mass function measured locally should be broadly consistent with the mass function inferred from the light of distant galaxies. All of these checks work at the factor of a few level, which is simultaneously reassuring and a reminder of how much uncertainty remains. Throughout tonight's exploration, the goal is not to leave you with a single confident number but with an honest picture of what we know, what we do not know, how the pieces fit together, and why the uncertainty in the estimate, far from being an embarrassment, is one of the most productive features of the problem, pointing precisely at the observations and analyses that will be most valuable for the future of the field. The question of how many stars exist is not merely a curiosity about an astronomical quantity. The answer to it constrains several of the most important open questions in science, and understanding what it constrains and how is worth doing before getting lost in the technical details of how the count is assembled. The most immediate connection is to astrobiology, the scientific study of the conditions under which life can arise, develop, and persist. The Fermi paradox, the observation that the universe appears vast and old enough that technological civilizations should be common and yet we detect no evidence of any beyond our own, has among its many proposed resolutions one that requires knowing the stellar census. Perhaps intelligent life is so rare that the universe has not yet produced more than one example within the observable volume. Whether that explanation is plausible depends critically on how many stars there are, because each star is a potential host for a planetary system, and each planetary system is a potential venue for chemistry, biology, and intelligence. If the observable universe contains 200 sextillion stars and each one has on average even one planet in a habitable zone with liquid water, the number of potentially life-supporting worlds is staggeringly large, and the absence of detected signals from other civilizations becomes correspondingly harder to explain by simple rarity. Conversely, if the number of suitable environments is much smaller due to various astrophysical filters, the stellar census defines the denominator of the probability calculation. The number of stars also constrains the amount of heavy element synthesis that has occurred in the observable universe. Every element heavier than lithium was produced inside stars and distributed through the universe when those stars died. The carbon in organic molecules, the oxygen in water, the iron in blood, the silicon in rock, all of this chemical diversity was forged in stellar interiors across the universe's history. Knowing how many stars have existed, including those that have already lived and died, tells us how much processing of hydrogen and helium into heavier elements has occurred, which tells us the maximum possible chemical complexity available to chemistry anywhere in the universe. The stellar census also connects to cosmology. The total amount of matter in stars, what astronomers call the stellar mass density of the universe, is one of the components of the universe's total matter budget. Comparing the stellar mass to the total matter, including the dark matter that constitutes roughly 85% of all matter, tells us how efficient the universe has been at converting matter into visible structures. Current estimates suggest that roughly 5% of the universe's total energy budget is in ordinary matter, and of that ordinary matter, roughly 5% has been converted into stars. Understanding these efficiency fractions requires knowing the stellar count. The stellar census also has implications for understanding the universe's energy budget over its history. Stars are the primary sources of electromagnetic radiation in the universe at wavelengths from the ultraviolet to the infrared. The total energy output of all stars over cosmic history is an enormous number that has heated the intergalactic medium, ionized the gas between galaxies, and driven the reionization of hydrogen that occurred in the first billion years after the Big Bang. The extragalactic background light, the accumulated glow of all starlight ever emitted, is a measurable quantity that constrains the total number of stars that have ever burned integrated over cosmic history. Measurements of the extragalactic background light from gamma-ray telescopes, which detect the attenuation of high-energy gamma rays from distant blazars as those gamma rays interact with the infrared photons of the background, give an integral constraint on the total stellar emissivity of the universe. This constraint is independent of the direct galaxy counts and the stellar population synthesis estimates, providing a completely different route to the same quantity. The consistency between different approaches is one of the strongest arguments that the stellar census estimates are in the right ballpark, even if the uncertainties remain large. Finally, the stellar count matters for understanding the cosmic chemical history. Each generation of stars converts hydrogen and helium into heavier elements and distributes them through the interstellar medium when stars die, enriching subsequent generations of star-forming gas with the products of previous stellar generations. The total amount of metal enrichment in the universe depends on how many stars have existed, how massive they were, and what fraction of their nucleosynthesis products were expelled rather than locked into remnants. The observed metallicity of stars, galaxies, and the intergalactic medium provides another constraint on the total stellar census integrated over history. Before any counting can begin, the object being counted must be defined. The definition of a star sounds trivially simple until you examine it carefully, at which point several boundary cases emerge that require precise physical criteria and that directly affect the resulting census. The standard physical definition of a star is a self-gravitating body that sustains or has sustained thermonuclear fusion of hydrogen in its core. This distinguishes stars from planets, which lack the mass to ignite hydrogen fusion, from brown dwarfs, which may sustain some limited fusion reactions but not the sustained hydrogen burning that defines the main sequence, and from the stellar remnants, white dwarfs, neutron stars, and black holes, that were once stars but are no longer fusing anything. The lower mass limit for hydrogen fusion is approximately 80 times the mass of Jupiter, corresponding to about 0.08 times the mass of the Sun, or roughly 80 solar masses. Below this threshold, the gravitational compression of the object is insufficient to heat the core to the temperature required for proton-proton chain reactions, approximately 10 million Kelvin. Objects below this threshold but above about 13 Jupiter masses are brown dwarfs, which can sustain deuterium fusion briefly but not the sustained hydrogen burning that characterizes genuine stars. Objects below 13 Jupiter masses are planetary mass objects. The upper mass limit is less precisely defined but appears to be somewhere in the range of 150 to 300 solar masses, above which radiation pressure from the star's own luminosity exceeds the gravitational force holding the star together. Stars above roughly 150 solar masses have been observed but are extremely rare and extremely short-lived, burning through their hydrogen fuel in less than a million years before exploding as hypernovae or collapsing to black holes. The practical contribution of ultramassive stars to the total stellar census is negligible because they are so rare and so short-lived. The distinction between stars and brown dwarfs at the lower mass boundary is genuinely blurry in practice. The boundary at 0.08 solar masses is not a sharp threshold below which hydrogen fusion is impossible and above which it proceeds normally. Objects near the threshold can sustain hydrogen fusion intermittently, and the distinction between a very low-mass star and a very high-mass brown dwarf may be impossible to determine observationally for specific individual objects without detailed knowledge of their internal structure. The boundary matters for the stellar census because the mass function, the distribution of how many objects form at each mass, rises steeply toward lower masses, and whether you count objects at the boundary as stars or not affects the total count by a meaningful fraction. The question of whether to count evolved stellar remnants as part of the stellar census also requires a decision. A white dwarf is the cooling core of a former Sun-like star, no longer fusing hydrogen but still containing all the carbon, oxygen, and other heavy elements that fusion produced. Neutron stars are even more compact remnants. Both are relevant to the complete history of stellar populations but are conventionally excluded from the stellar census, which typically counts currently active hydrogen-fusing stars and excludes remnants. The choice is conventional rather than physically motivated, and some discussions of the total stellar inventory include or separately account for the vast population of remnants. The transition between pre-main sequence stars and zero-age main sequence stars adds another subtlety to the definition. A protostar, the object formed during the initial gravitational collapse of a gas cloud before hydrogen fusion has ignited, is not yet a main sequence star but is on its way to becoming one. Should protostars be counted in the stellar census? The conventional answer is no. The census is of objects currently on the main sequence fusing hydrogen, not of objects in earlier evolutionary stages. But this means that the measured stellar population is a snapshot of a dynamic situation in which stars are continuously forming and the current number differs from the number that will exist in a billion years. The time a star spends on the main sequence, fusing hydrogen in its core, is inversely related to its mass in a steeply nonlinear way. A star like the Sun spends about 10 billion years on the main sequence. A star 10 times the mass of the Sun spends only about 20 million years. A star at the bottom of the main sequence, the least massive red dwarf, may spend more than 1 trillion years, 100 times the current age of the universe. This means that for any current stellar census, the entire population of red dwarfs that has ever formed is still present, while the massive stars that existed 10 billion years ago are all long dead and absent from today's count. This evolutionary accounting has direct consequences for the census. The current stellar population is heavily dominated by the accumulated survivors of billions of years of star formation, most of them low-mass stars that live so long they are essentially permanent on cosmic timescales, augmented by the recently formed massive stars whose lifetimes are short enough that their current presence reflects star formation within the last few tens of millions of years. The mass function of the current stellar population therefore differs from the initial mass function of star formation, with the massive end depleted by deaths and the low-mass end augmented by the survivors of all previous star-forming epochs. Counting the stars in the Milky Way is both the most direct component of the stellar census and, paradoxically, among the most difficult, because we are inside the object being counted. Mapping the distribution of stars across a disk-shaped galaxy from a point embedded within the disk is like trying to count the trees in a forest from a position somewhere in the middle, with the additional complication that some portions of the forest are obscured by fog and others are so distant that individual trees cannot be resolved from the background. The most direct way to count stars is to observe every star in a complete, well-defined volume of space and measure the number. This works reasonably well in the solar neighborhood, the region within a few hundred light-years of the Sun, where individual stars can be resolved by current telescopes. Within 25 light-years of the Sun, approximately 100 systems have been catalogued containing about 130 individual stars, and the catalog is estimated to be reasonably complete for main sequence stars of solar mass and above. The low-mass red dwarf population even within this small radius has been revised upward with each new survey, as faint red dwarfs that were missed in earlier less sensitive surveys were discovered. Extrapolating from the solar neighborhood to the full galaxy requires knowing the galaxy's geometry and the way stellar density varies across it. The Milky Way is a barred spiral galaxy with a diameter of roughly 100 to 120,000 light-years and a thickness in the disk of a few thousand light-years, though the disk thickens at larger galactic radii. The total disk area is enormous, and the stellar density varies significantly across it, higher near the center, where a dense bar and bulge concentrate billions of stars in a region only a few thousand light-years across, and lower in the outer disk, where star formation is less efficient and the stellar population is sparser. The galactic center is essentially invisible at optical wavelengths because the intervening dust in the disk absorbs and scatters the light before it reaches us. Infrared and radio observations, which penetrate the dust far more effectively, reveal a stellar density in the central few hundred light-years orders of magnitude higher than in the solar neighborhood. The nuclear star cluster surrounding the central supermassive black hole, Sagittarius A*, has a stellar density of perhaps 1 million stars per cubic parsec, compared to about 0.003 stars per cubic parsec in the solar neighborhood. Current best estimates for the total stellar content of the Milky Way range from about 100 billion to 400 billion stars, with the large uncertainty primarily driven by three factors: the uncertain stellar density profile of the galactic bulge, the incompleteness of surveys for low-mass stars throughout most of the disk, and the difficulty of observing the far side of the disk where dust extinction is most severe. The stellar content of the galactic bulge presents a particular challenge. The bulge, a roughly ellipsoidal concentration of stars at the galactic center, contains a substantial fraction of the Milky Way's total stellar mass but is heavily obscured by dust at optical wavelengths and has a complex mix of stellar populations representing different epochs of star formation. Near-infrared surveys, particularly the VISTA variables in the Via Lactea survey and the IRAC Galactic Center survey from the Spitzer Space Telescope, have mapped the stellar distribution in the bulge with increasing completeness, but converting the observed stellar density to a total stellar count requires models of the three-dimensional structure of the bulge and of its stellar population. The thin disk and thick disk components of the Milky Way have been more thoroughly characterized by a combination of photometric and spectroscopic surveys. The thin disk, which contains most of the young stars and the ongoing star formation, has a vertical scale height of roughly 300 to 400 parsecs, meaning the stellar density decreases by a factor of E roughly every 300 to 400 parsecs above or below the midplane. The thick disk, an older and kinematically hotter component with a scale height of about 1 kiloparsec, contains a significant fraction of the total disk stellar mass despite its lower density at the midplane. Adding together the best estimates for each structural component of the Milky Way, the thin disk, the thick disk, the bulge, the stellar halo, and the nuclear star cluster around the central black hole, gives a total stellar count with a genuine and acknowledged uncertainty. The most recent comprehensive estimates, taking advantage of Gaia data and infrared surveys, suggest a total of roughly 2 to 300 billion stars in the Milky Way, with the uncertainty dominated by the poorly determined density profile of the inner bulge and by the completeness corrections for low-mass stars throughout the disk. The most powerful general tool for counting stars is not direct enumeration, which becomes impossible for galaxies beyond the nearest few, but rather the use of stellar luminosity as a proxy for stellar population. If you can measure a galaxy's total luminosity and you know what kinds of stars produce that luminosity, you can work backward to infer the total number of stars. This tool, called stellar population synthesis, is the workhorse of extragalactic stellar astronomy and underlies most of the stellar census for the observable universe beyond the Milky Way and its immediate neighbors. The foundation of stellar population synthesis is the understanding that different types of stars contribute very differently to a galaxy's total light output. Massive, luminous, blue stars, the O and B-type stars, are individually among the brightest objects in any galaxy and dominate the ultraviolet output. A single O-type star can outshine the Sun by a factor of 1,000,000 and produce more light in its lifetime of a few million years than the Sun will produce in its 10 billion-year main sequence life. But these brilliant, short-lived stars are extraordinarily rare. For every O-type star, there are perhaps 1,000,000 or more of the dim red M-type dwarf stars. The M-dwarf stars, which are individually 10,000 to 100,000 times less luminous than the Sun, are so common that they may constitute 70 to 80% of all stars by number. Yet because each one is so faint, the contribution of the entire M-dwarf population to a galaxy's total optical luminosity may be only a few percent, easily swamped by the combined light of the rarer but brighter giant and supergiant stars. This creates a fundamental difficulty for stellar census work. The stars that are most abundant and therefore matter most for the total count contribute least to the observable luminosity, while the stars that dominate the light are rare enough to be individually countable in the local universe but too few in number to drive the total star count. The stellar luminosity function describes quantitatively how many stars exist per unit volume at each level of intrinsic luminosity. Measuring it requires a complete survey of stars within a well-defined volume, with distances determined from parallax measurements or other methods reliable enough to convert observed brightness into intrinsic luminosity. The luminosity function has been measured for the solar neighborhood with reasonable precision and shows the expected steep rise toward lower luminosities. There are roughly 100 times more stars at 1/10 solar luminosity than at 10 times solar luminosity. Extending this measurement to more distant regions requires corrections for the many stars too faint to be detected at those distances, a correction that requires knowing the shape of the luminosity function at the faint end. The faint end of the luminosity function, in the red dwarf regime, is precisely where the measurement is most uncertain and most important for the total stellar count. Getting this right is the single most important technical problem in the stellar census. The stellar luminosity function's importance for the stellar census cannot be overstated. The function is typically plotted as the number of stars per cubic parsec per magnitude interval, where magnitude is a logarithmic measure of luminosity. The resulting curve rises steeply toward fainter magnitudes, meaning the faint end of the luminosity function, corresponding to the least luminous and least massive stars, is where the vast majority of the stellar population is concentrated. Measuring the luminosity function accurately requires a sample of stars whose distances are known independently of their brightness, so that apparent brightness can be converted to intrinsic luminosity without circularity. The Hipparcos satellite, which measured parallaxes for about 120,000 nearby stars in the 1990s, provided the foundational parallax database for luminosity function work in the solar neighborhood, enabling precise distance-calibrated measurements for all stellar types bright enough to be detected within a few hundred parsecs. The Gaia satellite has extended this database by more than a factor of 10,000 in sample size, providing parallaxes for 1.7 billion sources. The shape of the luminosity function at the faint end, below about 1/10 solar luminosity, corresponding to stars with masses below about 0.2 solar masses, has been measured using volume-complete samples of nearby stars where even the faintest M-dwarfs can be individually detected. These measurements confirm the steep rise toward lower luminosities but also reveal a turnover or flattening at the very faint end, near the hydrogen burning limit, suggesting that the number of stars does not continue to increase without bound toward lower masses. The location and shape of this turnover is important for the total stellar census because it determines how many objects exist near the lower mass boundary of the stellar sequence. The conversion between luminosity function and number density requires integrating over the entire luminosity range, from the most luminous supergiants to the least luminous red dwarfs, weighted by the number density at each luminosity. The total number density of stars in the solar neighborhood derived from this integration is roughly 0.1 stars per cubic parsec, or equivalently about 1 star per 10 cubic parsec volume, a figure that serves as the anchor point for all larger-scale stellar census work. One of the most consistent patterns in the history of stellar astronomy is that whenever astronomers have developed new tools to see fainter objects or to look through intervening obscuration, they have found more stars than the previous estimate suggested. This pattern has repeated itself so many times, from Galileo's resolution of the Milky Way into individual stars, to the construction of the first photographic sky surveys, to the development of infrared astronomy, to the current generation of space telescopes, that it deserves explicit examination as a systematic feature of how the field has developed. The naive expectation would be that early estimates of the stellar population were too low because early telescopes could only detect bright stars and therefore missed the faint majority. This is partly correct but incomplete. The more interesting reason that estimates have risen is that each new observational capability has not merely detected already expected faint stars in already known categories but has revealed entire classes of objects that were not previously recognized as stars or were not known to exist at all. The story of M-dwarf discovery illustrates this well. In the era of photographic sky surveys in the early 20th century, the number of known stars was dominated by what could be detected on photographic plates, which were most sensitive to blue light and therefore most effective at finding hotter, bluer stars. The population of very red M-dwarfs was systematically undercounted because they appeared so faint on blue-sensitive plates that many fell below the detection threshold even at nearby distances. The development of more sensitive red and infrared detectors in the latter half of the 20th century gradually revealed a larger and larger population of red dwarfs in the solar neighborhood, pushing the estimated stellar number density upward with each successive survey. The discovery of brown dwarfs in 1995, after decades of searching, did not add to the stellar count since brown dwarfs do not meet the definition of stars, but it did reveal that the mass function continued to rise below the hydrogen burning limit, with significant numbers of substellar objects at every mass down to at least a few Jupiter masses. This discovery influenced thinking about how many objects near the stellar boundary existed and whether some of them, previously classified as stellar from their luminosity, might actually be brown dwarfs seen at close range. More recent surveys from space, particularly from the Gaia satellite and from infrared observatories, have continued the historical trend of finding more stars than expected. Within the solar neighborhood defined by the nearest 100 light-years, new stars are still being added to catalogs as surveys improve. Several nearby red dwarf systems were discovered in the 21st century at distances so small that they would certainly have been found earlier had earlier instruments been sensitive enough. The most recent nearby discovery before the Gaia era was WISE 0855-0714, a brown dwarf at about 7 light-years, discovered in 2014 in Wide-Field Infrared Survey Explorer data that was sensitive enough to detect objects nearly too cold to glow at any previously accessible wavelength. The most dramatic recent case of finding more stars than expected came from studies of massive elliptical galaxies using gravitational lensing and detailed spectroscopy. In 2010, Peter van Dokkum and Charlie Conroy published observations suggesting that massive elliptical galaxies, which had previously been modeled as containing stellar populations similar to those of old metal-rich stars in the Milky Way's bulge, actually contained far more low-mass red dwarf stars than previously assumed. Their evidence came from spectral features in the infrared that are sensitive to the surface gravity of stars, and therefore to whether stars are dwarf stars or giant stars, features that showed a signature consistent with a large dwarf star population in excess of what standard mass functions predicted. If massive elliptical galaxies are more bottom-heavy, meaning they have more low-mass stars per unit of total stellar mass, than the solar neighborhood's population suggests, the total number of stars in the universe would be significantly larger than census estimates based on locally calibrated mass functions. Van Dokkum and Conroy estimated that the correction could be a factor of several, potentially pushing the total stellar count upward by a factor of 3 to 5 from standard estimates. Subsequent studies have been more mixed in their conclusions, with some supporting the bottom-heavy mass function in ellipticals and others finding results more consistent with the locally calibrated function, and the question remains unresolved. The consistent pattern of upward revision in the stellar count over the history of astronomy suggests that epistemic humility about the current best estimate is warranted. Not only might the galaxy count be substantially higher than standard estimates, and not only might the mass function be more bottom-heavy in some galaxy types than locally calibrated, but there may be additional classes of stars or near-stellar objects that current surveys are systematically missing. The history of the field says to expect more, not to trust that current instruments have finally seen everything there is to see. Red dwarf stars, classified astronomically as M-type main sequence stars, are the universe's most numerous stars by a margin that is not close. Current estimates suggest that red dwarfs constitute somewhere between 70 and 80% of all hydrogen-fusing stars in the Milky Way by number, and likely a similar fraction throughout the observable universe. They are also among the longest-lived, burning their hydrogen so slowly that no red dwarf formed since the Big Bang has yet had time to exhaust its fuel and leave the main sequence. Every red dwarf that has ever formed still exists. They are the universe's most persistent stars, and they are almost completely invisible to the naked eye. The most famous red dwarf in the sky is Proxima Centauri, the nearest star to the Sun at a distance of approximately 4.24 light-years. Proxima Centauri has a mass of about 0.12 solar masses, a luminosity of about 0.0017 solar luminosities, and a surface temperature of approximately 3050 Kelvin, giving it a faint reddish glow. Despite being the nearest star other than the Sun, Proxima Centauri has an apparent magnitude of about 11.1, far too faint to see without a telescope. It would be invisible even with binoculars under most conditions. The second nearest star, Barnard's star, is similarly invisible to the naked eye at an apparent magnitude of about 9.5. The invisibility of red dwarfs to unaided observation has had profound consequences for the history of astronomical knowledge. Human intuitions about the night sky are built on what can be seen without optical aids, which is an extremely biased sample of the stellar population. The naked eye can detect roughly 6,000 stars under ideal conditions, and the majority of these are relatively bright, nearby stars of spectral types K, G, F, A, and B. The actual distribution of stellar types weighted by number would be unrecognizable to a naked eye observer. Instead of a sky sprinkled with vivid blue, white, yellow, and red giants, the true census reveals that almost every star within any volume of space is a dim red dwarf. The consequence for stellar surveys is that any survey based on apparent brightness rather than volume-limited selection will dramatically undercount M dwarfs. A magnitude-limited survey, one that detects all stars brighter than some apparent magnitude threshold, inherently oversamples nearby bright stars and undersamples distant faint ones, and because M dwarfs are individually so faint, most of them fall below any reasonable magnitude limit at distances beyond a few tens of light-years. Converting the detected stellar sample back to a true number density requires applying large corrections for the missed population. The mass at which red dwarfs become too low mass to sustain hydrogen fusion is about 80 times the mass of Jupiter, or roughly 0.08 solar masses. At this boundary, the hydrogen burning rate drops to effectively zero. Objects below this limit are brown dwarfs. Distinguishing which observed objects fall on which side of this boundary, and getting the number count right for objects near the boundary, is one of the genuine technical challenges of the stellar census. The implications of red dwarf dominance for the stellar census extend to the chemical evolution of the galaxy in an interesting way. Because red dwarfs have such long main sequence lifetimes, they are the primary long-term repository of the material locked into stars. The carbon, oxygen, and other heavy elements incorporated into red dwarfs when they formed will remain locked inside them for timescales far exceeding the current age of the universe. Massive stars, by contrast, live briefly and return most of their material to the interstellar medium through stellar winds and supernova explosions, enriching the gas from which subsequent generations of stars form. The fraction of the galaxy's total mass in stars that is currently locked in red dwarfs, and therefore unavailable for further recycling, is substantial. A red dwarf of 0.1 solar masses forming in the first billion years of the Milky Way's history will still be on the main sequence in another trillion years, having never ejected significant material back into the interstellar medium, because red dwarfs are too low mass to drive significant stellar winds or to end as supernovae. This means that the galaxy's reserve of material available for new star formation has been progressively depleted not only by the creation of stellar remnants but also by locking material into long-lived red dwarfs that will not be recycled on any timescale relevant to galaxy evolution. The astrobiological significance of red dwarf abundance has attracted considerable attention since the discovery that many red dwarfs host compact planetary systems, including planets in habitable zones where liquid water might exist on surfaces. The TRAPPIST-1 system, orbiting a red dwarf at about 39 light-years from the Sun, contains 7 known planets including 3 in the habitable zone, all discovered by transit photometry. The frequency of such systems, combined with the fact that red dwarfs are so much more numerous than solar-type stars, has dramatically increased estimates of the number of potentially habitable planets in the galaxy. The European Space Agency's Gaia mission, launched in December 2013 and placed in an orbit around the Sun-Earth Lagrange Point 2, represents the most ambitious and productive stellar census mission in history. Its primary instrument is an astrograph, a device for measuring extremely precise positions and motions of stars on the sky, and its primary science objective has been to measure the parallaxes, proper motions, and radial velocities of the largest sample of stars ever systematically observed from space. Gaia measures stellar positions with a precision that in the best cases reaches a few tens of microarcseconds, roughly comparable to measuring the diameter of a human hair from a distance of 1,000 kilometers. This extraordinary precision, achieved through careful calibration of the satellite's attitude, thermal stability, and optical path, allows parallax measurements of stars at distances up to several thousand light-years with enough accuracy to determine distances to better than 10%. For the brightest and most nearby stars, the parallax precision translates to distance determinations better than 1%. Gaia's first full data release, containing parallaxes and proper motions for about 1.7 billion sources detected in the satellite's first 22 months of operation, transformed the landscape of stellar astronomy. Subsequent data releases have added radial velocity measurements from the onboard spectrograph, astrophysical parameters including surface temperature and luminosity, and photometric data in 2 additional wavelength bands that enable color magnitude diagram analysis for hundreds of millions of stars simultaneously. The third Gaia data release in 2022 contained astrophysical parameter estimates for approximately 470 million sources and radial velocities for 34 million stars. What Gaia has revealed about the Milky Way's stellar population extends far beyond the improved statistics. The satellite's precise proper motion measurements have allowed the identification of stellar streams, groups of stars moving through the galaxy with similar velocities that betray a common origin, in a satellite galaxy or star cluster that was disrupted and absorbed by the Milky Way billions of years ago. Several major accretion events in the Milky Way's history have been identified through the kinematic signatures they left in the current stellar population, including the Gaia-Enceladus sausage merger that occurred roughly 10 billion years ago and contributed a substantial fraction of the current interstellar halo. For the stellar census specifically, Gaia has provided the most reliable distance-calibrated sample of stars ever assembled, enabling the most accurate measurements of the local stellar luminosity function in the Milky Way's disk. The catalog is complete, meaning it has detected essentially every star above a certain brightness limit, out to several hundred parsecs for the brighter end of the stellar distribution and to tens of parsecs for the faintest red dwarfs. Within this complete volume, the stellar density and mass function can be measured with unprecedented accuracy, providing the anchor point from which larger-scale estimates are extrapolated. The Astrophysical Parameters Catalog released with Gaia Data Release 3 represents a particularly important resource for the stellar census. By analyzing the multiband photometry and spectra from the radial velocity spectrometer for hundreds of millions of sources, the Gaia team has estimated surface temperatures, luminosities, chemical compositions, and evolutionary states for a sample of stars large enough to characterize the stellar population across much of the Milky Way's disk. This enables not just a stellar count but a demographic census, how many stars of each type, at each evolutionary stage, with what range of chemical compositions, exist in the surveyed volume. The Gaia data have also revealed unexpected structure in the Hertzsprung-Russell diagram, the diagram of stellar luminosity versus surface temperature that has been the primary tool for understanding stellar evolution since the early 20th century. Several previously underpopulated or unknown regions of the diagram are now populated by stars in numbers large enough to characterize, revealing stellar populations in unusual evolutionary stages that were either too rare or too faint to study before Gaia. The white dwarf cooling sequence, in particular, now contains enough well-characterized members to study in detail the bifurcation into different tracks that reflects different atmospheric compositions and evolutionary histories. The proper motion measurements from Gaia have implications for the stellar census that go beyond simple counting. By tracking the motions of stars across the sky, Gaia identifies stars with similar space motions that are moving together as a coherent group, betraying a common origin in a dissolved star cluster or association. Many such groups have been discovered in the Gaia data that were not previously known, revealing that the galaxy's stellar disk has a complex history of star formation in clustered environments rather than in isolation. The census of dissolved clusters contributes to understanding the initial conditions under which the current stellar population formed and how those conditions varied with location and time in the galaxy's disk. Any attempt to count the stars in the Milky Way confronts an obstruction that has no analog in the counting of galaxies or other objects where we have an unobstructed view. The galaxy itself is filled with dust that absorbs and scatters starlight, making enormous fractions of the galactic disk effectively opaque at visible wavelengths. Understanding the scale of this obstruction and the methods used to work around it is essential for understanding why the stellar census of our own galaxy remains uncertain even after decades of intensive study. Interstellar dust consists of tiny particles ranging from a few nanometers to roughly 1 micrometer in size, composed primarily of silicates and carbonaceous material. These particles absorb visible and ultraviolet light and re-emit the absorbed energy at infrared wavelengths. The opacity of interstellar dust to visible light is roughly proportional to the inverse of wavelength, meaning blue light is absorbed and scattered more efficiently than red, and infrared light penetrates dust columns that are completely opaque at visible wavelengths. The practical consequence for stellar surveys is dramatic. Looking from the solar system toward the galactic center, a line of sight that passes through about 8 kiloparsecs of the galactic disk, the dust extinction at visible wavelengths is roughly 30 magnitudes. A magnitude of extinction corresponds to a factor of about 2.5 reduction in apparent brightness, so 30 magnitudes corresponds to a factor of 10 to the 12th in brightness reduction. A star as luminous as the Sun, located at the galactic center, would appear roughly 200 million billion times fainter than it would appear if there were no dust, making it completely undetectable with any optical telescope even in principle. Infrared and radio observations largely circumvent this problem. Near-infrared light at wavelengths around 2 micrometers suffers only a few magnitudes of extinction toward the galactic center, making infrared surveys vastly more effective at penetrating the disk. The 2-micron all-sky survey, completed in 2001, provided full sky coverage in 3 near-infrared wavelength bands and revealed the stellar population in the inner galactic plane far more completely than any previous optical survey. Subsequent infrared surveys with larger telescopes, including the Vista Variables in the Via Lactea survey and the Glimpse survey with the Spitzer Space Telescope, have added further detail. Even infrared surveys are not perfect penetrators of the densest molecular clouds, where dust columns are thick enough to extinguish even infrared light significantly. The densest star-forming regions in the galaxy are essentially invisible even in the near-infrared, and the stars forming within them cannot be observed until they eventually clear the surrounding material. The total contribution of these highly obscured regions to the galactic stellar inventory requires modeling rather than direct observation, introducing additional uncertainty. The three-dimensional distribution of dust in the Milky Way has been mapped with increasing resolution using multiple approaches. One approach uses the reddening of stars with known distances, because dust reddens starlight preferentially at shorter wavelengths. A star whose intrinsic color is known from its spectral type will appear redder than expected if dust lies along the line of sight, and the degree of reddening constrains the dust column. With large samples of stars at different distances, the three-dimensional dust density can be inverted from the reddening measurements. Gaia's photometric data for 1 billion stars has enabled three-dimensional dust maps at unprecedented resolution and coverage. A complementary approach uses the far-infrared emission from the dust itself. Warm dust, heated by the interstellar radiation field, emits radiation at wavelengths of tens to hundreds of micrometers that can be detected by space-based infrared telescopes. The Planck satellite's all-sky survey at millimeter and sub-millimeter wavelengths provides a map of the total dust column density integrated along each line of sight, while the Herschel Space Observatory's surveys of the galactic plane provided higher resolution maps in specific regions. Combining far-infrared emission maps with dust reddening measurements from stars gives a more complete picture of the dust distribution. Even with the best current dust maps, converting observed stellar density in dusty regions to a corrected stellar density requires assumptions about the dust-to-gas ratio and the relationship between dust mass and dust opacity that carry uncertainties of tens of %. The regions of highest uncertainty are also the regions of highest stellar density, the molecular cloud complexes in the galactic plane where the next generation of stars is forming. The contribution of these most obscured regions to the total galactic stellar count is therefore one of the less well-determined components of the Milky Way census, and improving it requires either better dust models or observations at wavelengths long enough to be unaffected even by the densest dust columns. The step from counting stars in the Milky Way to estimating the number of stars in the observable universe requires knowing how many galaxies there are and how many stars each galaxy contains. Both of these quantities are themselves uncertain, and the product of two uncertain quantities produces an estimate whose uncertainty is the combination of the uncertainties in its factors. The uncertainty in the galaxy count is particularly consequential because it was revised dramatically upward in 2016, and the implications of that revision have not yet been fully absorbed into all discussions of the stellar census. The number of galaxies in the observable universe was estimated for decades at roughly 100 billion, a figure derived from deep surveys with the Hubble Space Telescope and extrapolated to the full sky. The Hubble Deep Field, a 10-day exposure of a tiny region of sky in 1995, revealed approximately 3,000 galaxies in a patch covering roughly 1/24 millionth of the full sky, implying roughly 70 billion galaxies in the observable universe at the depth of that survey. Deeper surveys found more galaxies per unit area, and estimates settled around 100 to 200 billion galaxies as the canonical number. In 2016, Christopher Consolis and collaborators published a paper in the Astrophysical Journal using a different approach. Rather than counting galaxies detected in deep surveys and extrapolating, they applied a model of galaxy merger history to estimate how many galaxies should have existed at various redshifts based on the observed rate at which galaxies merge over time. Their conclusion was that the number of galaxies in the observable universe is approximately 2 trillion, nearly 10 times the previous estimate. The difference arises because many galaxies in the early universe were small, faint protogalactic fragments that have since merged into larger structures and that current surveys, even the deepest ones, cannot detect. The 2 trillion number is not universally accepted and represents a modeling-dependent estimate rather than a direct count. Some cosmologists argue that the model assumptions are uncertain enough that the true number could still be closer to the traditional 100 billion figure. The James Webb Space Telescope, with its unprecedented infrared sensitivity and the ability to detect galaxies in the first few 100 million years after the Big Bang, is providing data that will eventually constrain the galaxy merger history with much higher precision and should allow a more reliable determination of the total galaxy count. For the stellar census, the difference between 100 billion and 2 trillion galaxies is enormous. If each galaxy contains an average of roughly 100 billion stars, 100 billion galaxies gives 10 to the 22 stars, while 2 trillion galaxies gives 2 times 10 to the 23 stars. The galaxy count uncertainty alone spans a factor of 10 in the total stellar number, dwarfing most other sources of uncertainty in the estimate. The methods used to count galaxies have evolved substantially over the decades. Early galaxy surveys relied on photographic plates, which recorded galaxy images along with stellar images and required human examination to classify objects as stars or galaxies. The development of digital imaging in the 1980s and 1990s, combined with increasingly sophisticated algorithms for source detection and classification, enabled automated surveys that could process millions of images and identify galaxies much more efficiently than visual inspection allowed. The Sloan Digital Sky Survey, which began operations in 2000 and has produced multiple generations of spectroscopic and photometric catalogs, has been one of the most productive galaxy surveys in history, measuring redshifts for more than 2 million galaxies and photometric data for hundreds of millions more. The survey's galaxy catalog covers roughly a quarter of the sky and extends to redshifts of order 1, corresponding to a look-back time of several billion years, providing the largest homogeneous galaxy sample for studies of large-scale structure, galaxy evolution, and the statistical properties of the galaxy population. For the deep fields that probe to the highest redshifts, the dominant challenge is not the number of detected objects but the completeness correction. How many galaxies exist at these redshifts that are too faint to be detected even in the deepest available exposures? This correction depends on the faint end of the galaxy luminosity function, the distribution of how many galaxies exist at each luminosity level, which at high redshift requires modeling rather than direct measurement. The steep faint end of the luminosity function means that for every detected galaxy there are many more below the detection threshold, and the ratio of detected to total depends sensitively on how steep the faint end is and where it cuts off. Different assumptions about the faint end slope lead to galaxy count estimates that differ by factors of several, which is a major contributor to the uncertainty in the total stellar census. For galaxies beyond the local group, individual stars cannot be resolved with current instruments, and the stellar census must be performed by analyzing the integrated light of the entire galaxy. This is a fundamentally different approach from the direct enumeration possible in the solar neighborhood, and it introduces different sources of uncertainty that require different mitigation strategies. The technique of stellar population synthesis begins with a library of theoretical stellar spectra, computed models of the light emitted by stars of different masses, temperatures, compositions, and evolutionary stages. By combining these individual stellar spectra in proportions specified by a model of the stellar population, a synthetic galaxy spectrum can be computed and compared to the observed spectrum of a real galaxy. The best-fitting combination tells you what mix of stellar types and ages is required to reproduce the observed light, from which the total stellar mass can be estimated. The relationship between a galaxy's total luminosity and its total stellar mass depends on what astronomers call the mass-to-light ratio, denoted with the symbol m/L. A galaxy made entirely of very old, dim red dwarf stars would have a high mass-to-light ratio, enormous mass but relatively little light. A galaxy with ongoing star formation, containing many young massive blue stars, would have a low mass-to-light ratio, a substantial amount of light coming from a relatively small contribution to the total mass. The mass-to-light ratio of a galaxy therefore encodes information about its star formation history and the current age distribution of its stellar population. Inferring the mass-to-light ratio from observations requires assumptions about the stellar initial mass function, the distribution of stellar masses at birth, which determines what fraction of the total mass ends up in bright, massive stars versus dim, low-mass stars. If the mass function has a higher proportion of low-mass stars than assumed, the mass-to-light ratio is higher and the inferred mass, and therefore the stellar count, is larger. Conversely, if the mass function is weighted toward higher masses, the mass-to-light ratio is lower and the stellar count is smaller. The mass-to-light ratio approach provides estimates of total stellar mass, which must then be converted to stellar number using an assumed average stellar mass. The average stellar mass in a population dominated by low-mass red dwarfs is roughly 0.3 to 0.5 solar masses. Dividing the total stellar mass by the average stellar mass gives the total number of stars, but this conversion is uncertain at the factor of several level because of uncertainty in both the mass-to-light ratio and the average stellar mass. The James Webb Space Telescope has already improved this situation by detecting the spectral signatures of evolved stellar populations in distant galaxies with higher signal-to-noise than previous instruments, providing better constraints on the stellar population synthesis models and reducing some of the systematic uncertainties in the mass-to-light ratio determinations. The uncertainty in stellar population synthesis results is further complicated by the age metallicity degeneracy, a fundamental ambiguity in the optical colors of stellar populations. An old, metal-rich population of stars can produce colors very similar to a younger, metal-poor population, because the effects of age and metallicity on stellar spectra are similar in the optical bands. Distinguishing between these possibilities requires spectroscopic observations at high signal-to-noise, which for distant galaxies requires long integration times on large telescopes and is therefore available for only a small fraction of the galaxy population. The majority of the galaxy census must rely on photometry alone, accepting the additional uncertainty from the age metallicity degeneracy. Infrared spectroscopy partially breaks this degeneracy because certain spectral features in the infrared are more sensitive to metallicity than to age, while others respond primarily to age. The James Webb Space Telescope's near-infrared spectrograph provides access to these diagnostic features for galaxies at redshifts where the features are shifted into observable wavelength ranges, enabling more reliable determinations of stellar population ages and metallicities than was possible with Hubble. The improved stellar mass estimates from Webb spectra are gradually propagating into more reliable mass-to-light ratios for different galaxy types, reducing one of the significant systematic uncertainties in the stellar census. Another approach to counting stars in distant galaxies uses gravitational lensing. When a foreground galaxy or galaxy cluster acts as a gravitational lens, it magnifies the images of background galaxies by factors that can range from a few to tens or hundreds in the most extreme cases. This natural magnification allows more detailed study of the stellar populations of distant galaxies than would otherwise be possible, effectively borrowing angular resolution from the gravitational optics of the foreground mass. The Hubble Frontier Field Survey specifically targeted galaxy clusters known to produce strong lensing, enabling much more detailed study of background galaxies at redshifts above 1 than would have been possible without the lensing amplification. The initial mass function, the distribution describing how many stars form at each mass, is one of the most important and most uncertain quantities in astrophysics. It is conventionally parameterized as a power law. The number of stars forming with a given mass per unit time is proportional to that mass raised to some negative power, meaning fewer high-mass stars form than low-mass ones for any given total mass of star-forming material. Edwin Salpeter published the first empirical measurement of the initial mass function in 1955, finding a power law slope of -2.35 for stars more massive than about 1 solar mass. This slope, called the Salpeter slope, has been confirmed many times over for the intermediate and high-mass end of the distribution and is one of the more robust empirical results in stellar astronomy. A slope of -2.35 means that for every star of mass 10 solar masses, there are roughly 10 to the power 2.35, or about 224, stars of 1 solar mass, and for every star of 1 solar mass, there are about 224 stars of 0.1 solar masses, if the slope continued unchanged into the low-mass regime. But the slope does not continue unchanged. Below about 1 solar mass, the initial mass function flattens, meaning fewer very low-mass stars form relative to what a continuation of the Salpeter slope would predict, though still more low-mass stars than high-mass ones. The flattening was first systematically studied by Pavel Kroppa and his collaborators in the 1990s and 2000s, leading to the Kroppa initial mass function that includes a broken power law with a shallower slope below about 0.5 solar masses. The exact shape of the mass function below about 0.3 solar masses is the most uncertain and most consequential part of the description. If the mass function continues to rise steeply into the brown dwarf regime and below, with large numbers of low-mass stars near the hydrogen burning limit, the total stellar count is much higher than if the function flattens or turns over at low masses. Observations in young star clusters, where the full mass function from the most massive stars down to brown dwarfs can be characterized in a single population, suggest that the function does flatten but does not turn over sharply in the stellar regime. The turnover, if it exists, appears to occur in the brown dwarf range rather than the stellar range, leaving the number of stars in the lowest stellar mass range genuinely uncertain. The question of whether the initial mass function is universal, the same in all environments across all time, is equally important and equally unresolved. Evidence from nearby star clusters and the solar neighborhood suggests a broadly similar shape across these environments, but evidence for variation comes from studies of elliptical galaxies, whose integrated light appears to require a bottom-heavy mass function, more low-mass stars per high-mass star, than what is observed locally. If massive elliptical galaxies, which contain a substantial fraction of all stellar mass in the universe, have systematically more low-mass stars than locally calibrated mass functions suggest, the total stellar count in the universe could be significantly higher than standard estimates. The theoretical understanding of why the initial mass function has the observed shape is an active research area that has made significant progress in recent years through high-resolution simulations of star formation in molecular clouds. The challenge is that stellar masses span a range from 0.08 to perhaps 300 solar masses, a factor of nearly 4,000, and the physical processes that determine where in this range any given star ends up involve the complex interplay of gravity, turbulence, magnetic fields, radiation feedback, and the chemistry of the molecular cloud environment. Simulations by Mark Krumholz, Stella Offner, and others have shown that the initial mass function can arise naturally from the turbulent fragmentation of molecular clouds without requiring fine-tuning of input parameters. The turbulent velocity field in a molecular cloud produces density fluctuations on a range of scales, and the Jeans mass, the minimum mass that can collapse under gravity given the local temperature and density, sets a characteristic mass for fragmentation. The peak of the initial mass function near half a solar mass corresponds roughly to the Jeans mass in the warm neutral medium that feeds star-forming molecular clouds, providing a theoretical explanation for why the characteristic stellar mass has the value it does. The predicted mass function from these simulations broadly matches the observed Kroppa or Chabrier forms, with a power law tail at high masses and a turnover at low masses. Whether the simulations correctly predict the behavior in extreme environments, such as the very high pressure, high metallicity, or high radiation field conditions found in the centers of massive elliptical galaxies, is less certain. It is precisely these extreme environments where observations suggest the mass function may differ from the locally calibrated form, and where better theoretical understanding could reduce the uncertainty in the total stellar census. The Hubble Deep Field of 1995 was one of the most consequential single observations in the history of astronomy. Then-director Robert Williams used his director's discretionary time to point the Hubble Space Telescope at a patch of sky in the Big Dipper region selected for having minimal contamination from foreground objects, and the telescope stared at this patch for 10 consecutive days, accumulating an exposure so deep that it reached galaxies a billion times fainter than the faintest stars visible to the naked eye. The resulting image showed approximately 3,000 galaxies packed into a region of sky smaller than a grain of sand held at arm's length. The scientific impact of the Hubble Deep Field went far beyond demonstrating that galaxies were numerous. It showed that the galaxy population at high redshift, corresponding to earlier epochs in cosmic history, had a different character from nearby galaxies, many more small, irregular, blue objects that appeared to be galaxies in the process of formation, and fewer large, settled spiral and elliptical galaxies of the kind that dominate the local universe. This morphological evolution of the galaxy population was the first direct visual evidence that galaxies have changed substantially over the age of the universe, growing through mergers and star formation from small protogalactic fragments to the large structures we see nearby. For the stellar census, the Hubble Deep Field and its successors, including the Hubble Deep Field South, the Great Observatory's Origins Deep Survey, the Extreme Deep Field, and the Hubble Frontier Fields, provided the observational foundation for estimates of how many galaxies exist and how the galaxy population has evolved with time. By comparing the observed number density of galaxies at different redshifts with cosmological models of galaxy formation and evolution, astronomers could infer the total stellar mass assembled at different epochs and extrapolate the current stellar mass density of the observable universe. The James Webb Space Telescope has extended these deep field observations to wavelengths and depths inaccessible to Hubble. Webb's infrared sensitivity and large mirror collect light from galaxies at redshifts greater than 10, corresponding to when the universe was less than 500 million years old, a regime where Hubble could only marginally detect the brightest examples. Webb's early release observations included a deep field image comparable in exposure time to the original Hubble Deep Field but covering much higher redshift galaxies, revealing a population of early galaxies with properties, masses, sizes, and stellar populations, that have surprised and in some cases puzzled cosmologists. Several early Webb galaxies appear more massive than expected for their age, suggesting that star formation began earlier and was more efficient in some environments than theoretical models predicted. These early Webb discoveries have not yet been fully integrated into the stellar census estimates, but they suggest that the total amount of star formation that occurred in the universe's first billion years may be somewhat larger than standard models assumed, potentially revising upward the total stellar inventory after accounting for the massive stars that formed early and have since died. The extreme deep field produced from combining 10 years of Hubble observations in the original Hubble Deep Field region represents the deepest optical image ever obtained with Hubble, reaching galaxies at distances of more than 13 billion light-years and exposing objects fainter than 31 on the magnitude scale. Analysis of this image revealed approximately 5,500 galaxies in a region covering roughly 4.7 square arc-minutes, and extrapolating to the full sky at this depth gives an estimate of roughly 200 billion galaxies within Hubble's reach. Crucially, the number of detected galaxies increases steadily from the shallowest to the deepest exposures with no sign of the number density turning over, suggesting that even the deepest Hubble exposures are still missing a significant fraction of the galaxy population. The faintest galaxies at the edge of Hubble's detection are numerous and blue, consistent with being young, compact, star-forming systems in the early universe that are the protogalactic building blocks from which today's larger galaxies assembled through mergers. These small, faint objects are not well characterized by Hubble at their detection threshold, contributing to the uncertainty in the faint end of the galaxy luminosity function and therefore in the total galaxy count. The James Webb Space Telescope's JADE survey, the JWST Advanced Deep Extragalactic Survey, has produced the deepest infrared images of any comparable area, revealing galaxy populations at redshifts above 10 that Hubble could not detect at all. Among the most striking Webb discoveries for the stellar census are several galaxies at redshifts between 8 and 12 that appear to have stellar masses of roughly 10 to the 10 solar masses or more, comparable to sizable present-day galaxies but assembled in a universe that was only 500 million to a billion years old. These massive early galaxies were not predicted in standard cosmological simulations and suggest that the efficiency of star formation in the first billion years of cosmic history may have been higher than previously thought. The most systematic way to count all the stars that have ever formed in the observable universe is to measure the rate at which stars were forming at each epoch in cosmic history and integrate that rate over time. This approach, studying what is called the cosmic star formation history, is complementary to the current stellar census and provides a cross-check on the estimates of how many stars currently exist. The cosmic star formation rate density, the total mass of new stars being formed per year per unit volume of the universe, has been measured as a function of redshift using several different observational tracers. The most widely used tracers are the ultraviolet luminosity of galaxies, which is produced by young massive stars and therefore traces recent star formation, and the infrared luminosity, which measures the ultraviolet light reprocessed by dust and is therefore sensitive to star formation in dusty galaxies that would be underestimated by ultraviolet measurements alone. The picture that has emerged from combining these tracers across many surveys and redshifts is one of the most important results in observational cosmology. The cosmic star formation rate was not constant over the universe's history. It was very low in the first billion years after the Big Bang, as the first galaxies were forming and assembling their gas supplies. It rose steeply to a peak around 10 billion years ago, when the universe was roughly 3 to 4 billion years old, an era sometimes called cosmic noon or the era of galaxy assembly. Since that peak, the star formation rate has declined by roughly an order of magnitude, reaching the relatively modest level of the present. The integrated star formation over cosmic history produces a total stellar mass, and comparing this with the observed stellar mass density today provides a consistency check. The integral should match the current mass accounting for the mass returned to the interstellar medium when stars die and for the mass locked up in stellar remnants. The agreement between these two approaches is good but not perfect, with residual discrepancies at the 10 to 30% level that reflect systematic uncertainties in both the star formation rate measurements and the current stellar mass estimates. For the total stellar census, the cosmic star formation history tells us not just how many stars currently exist but how many have existed over all of cosmic history. The number of stars that have ever formed and died before the present epoch is probably comparable to the number that currently exist, meaning the total number of stars that have ever lived in the observable universe is roughly twice the current stellar population, or somewhere around 4 to 5 times 10 to the 23rd stars that have burned hydrogen at some point in the universe's 13.8 billion year history. The decline of cosmic star formation since the peak at a redshift of about 2, corresponding to 10 billion years ago, reflects the progressive depletion of the cold gas supply available for star formation in galaxies. Galaxies can obtain new gas supplies from three sources: the accretion of pristine gas from the intergalactic medium, the recycling of gas expelled from dying stars back into the interstellar medium, and a merger with gas-rich companion galaxies. As the universe has aged, the intergalactic medium has become more fully ionized and heated, making it harder for gas to cool efficiently and fall into galaxies. The merger rate has declined as galaxies spread apart due to the expansion of the universe. And the fraction of gas available for recycling has decreased as more material has been locked into long-lived stars and stellar remnants. The result is a universe whose star formation rate has been declining for the past 10 billion years and will continue to decline. The current rate of star formation in the Milky Way, roughly 1 to 3 solar masses per year, is low by historical standards. At the peak of cosmic star formation, the universe was forming stars at a rate roughly 10 times higher per unit volume. Extrapolating the decline forward, the universe's star formation rate will continue to fall for billions of years before asymptotically approaching zero as gas supplies are exhausted. The integrated future star formation, the total mass of stars that will ever form from now until star formation effectively ceases, is estimated to be comparable to the current stellar mass, meaning that the universe is roughly halfway through its star-forming epoch in terms of total stellar mass accumulated. This estimate depends on assumptions about how long the declining star formation rate continues and how efficiently future star-forming gas is converted to stars, but it suggests that the final total of stars ever formed in the observable universe will be roughly twice the current census number, somewhere around 4 to 5 times 10 to the 23rd. When discussing how many stars there are in the universe, the conventional answer refers to currently active hydrogen-fusing stars. But the universe also contains an enormous population of stellar remnants, objects that were once stars but have completed their nuclear burning and collapsed or expanded into their final configurations. This remnant population is rarely included in the stellar census but is relevant to the complete picture of what the universe's past stellar activity has produced. White dwarfs are the most common type of stellar remnant. Every star with a final core mass below approximately 1.4 solar masses, the Chandrasekhar limit, ends its life as a white dwarf, a ball of carbon and oxygen roughly the size of Earth, supported against gravitational collapse by electron degeneracy pressure rather than nuclear burning, slowly cooling over billions to trillions of years. The Sun will become a white dwarf in roughly 5 billion years. Because the white dwarf cooling timescale is comparable to or longer than the current age of the universe for the coolest examples, white dwarfs retain a memory of the stellar population that produced them. Counting them and measuring their temperatures provides a chronometer of the history of star formation in any stellar system. The Milky Way is estimated to contain roughly 10 billion white dwarfs, most of them too faint to appear in any current all-sky catalog. The Gaia satellite has detected hundreds of thousands of white dwarfs in its astrometric catalog, selected by their characteristic parallax-adjusted positions on the Hertzsprung-Russell diagram rather than by any special spectroscopic observation. These detections provide a direct census of the white dwarf population within a few hundred parsecs and allow extrapolation to the full galaxy. Neutron stars are the remnants of more massive stars, those with main sequence masses between roughly 8 and 20 solar masses that end their lives in core collapse supernovae, leaving behind a ball of neutrons with a mass between about 1.2 and 2.2 solar masses compressed into a sphere roughly 12 to 15 kilometers in radius. The extreme density, comparable to that of an atomic nucleus, allows neutron stars to rotate at extraordinary rates while maintaining structural integrity. The fastest known pulsar spins at 716 rotations per second. The Milky Way is estimated to contain roughly 1 billion neutron stars, of which only about 3,000 are currently detectable as pulsars because the pulsar beam must sweep across Earth to be detected. Stellar mass black holes, the remnants of the most massive stars, are even harder to find than neutron stars. They are completely dark except when accreting mass from a companion star or from ambient gas, making isolated black holes essentially invisible against the sky background. The gravitational wave detections of merging black hole binaries have provided a new way to count them statistically, from the rate of merger detections and the estimated volume of the universe surveyed, the number density of merging black hole binaries can be inferred and used to constrain the total black hole population. The white dwarf population in the solar neighborhood has been studied extensively enough to provide useful constraints on the Milky Way's star formation history. The luminosity function of white dwarfs, the distribution of how many white dwarfs exist at each luminosity, has a characteristic downturn at low luminosities that reflects the finite age of the universe. The oldest white dwarfs have had only 13 billion years to cool, so they can only have reached temperatures corresponding to a specific minimum luminosity. The luminosity at which the white dwarf luminosity function turns down is therefore a clock measuring the age of the population that produced the white dwarfs. Studies of the white dwarf luminosity function in globular clusters, ancient stellar systems whose ages are known independently from main sequence turnoff calculations, confirm the consistency of the white dwarf cooling ages with the expected ages of the clusters. The same technique applied to the field white dwarf population in the solar neighborhood gives an estimate for when the local thick disk stars formed, roughly 9 to 10 billion years ago, consistent with other age determinations. For the stellar census, the white dwarf population serves as a lower bound on the number of stars that have already died. If there are 10 billion white dwarfs in the Milky Way, there must have been at least 10 billion main sequence stars that lived and died during the galaxy's history in addition to the current stellar population. Combined with estimates of the neutron star and black hole populations, the total number of stellar remnants places a lower bound on the past stellar population that is a significant fraction of the current population, consistent with the prediction from stellar evolution models that the number of stars that have died in the Milky Way is comparable to the number currently alive. The boundary between the least massive stars and the most massive brown dwarf sits at roughly 80 times the mass of Jupiter, or about 1/12 the mass of the Sun, and this boundary is important for the stellar census for two reasons. First, objects near this boundary are physically similar whether they are just above or just below it, and observational classification requires detailed physical modeling of individual objects rather than simple luminosity or color measurements. Second, the mass function rises steeply toward lower masses all the way through the stellar regime, and whether it continues to rise or turns over at the stellar brown dwarf boundary directly affects the total number of objects in the lowest mass stellar category. Brown dwarfs were predicted theoretically in the 1960s by Shiv Kumar and later by Jill Tarter, but their discovery required waiting for detector technology sensitive enough to detect such faint, red objects. The first confirmed brown dwarf, Tide 1, was discovered in the Pleiades star cluster in 1995 by a team at the Instituto de Astrofísica de Canarias. In the same year, Gliese 229b was confirmed as a brown dwarf companion to a nearby red dwarf, displaying the methane absorption bands in its spectrum that had been predicted as characteristic of objects cool enough to allow atmospheric methane rather than the simpler molecules typical of stellar atmospheres. Since 1995, thousands of brown dwarfs have been identified through wide-field infrared surveys. Brown dwarfs span a range of surface temperatures from just below the hydrogen burning limit at about 1500 to 2000 Kelvin, in the spectral class called L dwarfs, down to the coldest known examples at about 250 Kelvin in the spectral class called Y dwarfs. The Y dwarfs, some of which are cooler than a kitchen oven, represent the extreme low-temperature end of substellar object discoveries and have been found almost exclusively in infrared survey data from space. The ratio of brown dwarfs to stars in the solar neighborhood is estimated at roughly 1 brown dwarf for every 4 to 6 stars, though this ratio has uncertainties because brown dwarfs are so faint at large distances that surveys are complete only within relatively small volumes. If this ratio holds throughout the galaxy, the total brown dwarf population of the Milky Way would be 20 to 60 billion, not contributing to the stellar census but representing a comparable number of objects to some fraction of the stellar population. For the stellar census, what matters is not the brown dwarf count itself but what the brown dwarf population tells us about the mass function near the stellar brown dwarf boundary. The fact that the mass function continues smoothly across the boundary, rising toward lower masses both above and below it, suggests that no dramatic pileup of objects just above the hydrogen burning limit is causing a systematic overcount or undercount of low-mass stars. The boundary is real physically but does not appear to produce a sharp feature in the observed mass function, supporting the extrapolations used in stellar census estimates. The spectral classification of brown dwarfs has been extended beyond the T-dwarf class to include the white dwarfs, objects with effective temperatures below about 500 Kelvin. At these temperatures, water condenses in the atmosphere and the infrared spectra show distinctive water-ice absorption features that are not present in warmer brown dwarfs. The coldest known white dwarf, WISE 0855-0714, has an effective temperature estimated at roughly 250 Kelvin, comparable to the average temperature of Earth's surface, making it the coldest known free-floating object outside the solar system. Its mass is estimated at roughly 3 to 10 Jupiter masses, placing it at or below the deuterium burning limit and making it either a very low-mass brown dwarf or a free-floating planetary mass object, depending on how the classification boundary is defined. The distinction between the least massive brown dwarfs and free-floating planetary mass objects presents the same kind of boundary problem as the distinction between the least massive stars and the most massive brown dwarfs. Objects at masses of a few Jupiter masses can form either through the gravitational collapse of a molecular cloud fragment, the process that forms stars and brown dwarfs, or through disk instability or other processes in a protoplanetary disk followed by ejection from the system, the processes that form planets. Whether a given free-floating object with a mass of 5 Jupiter masses is a failed brown dwarf or an ejected planet cannot usually be determined from its current properties alone. For the stellar census, the existence of this boundary is relevant because it constrains our understanding of where the mass function turns over at the low end. If the mass function continues to rise through the brown dwarf regime and into the planetary mass regime, with comparable numbers of objects at each mass per logarithmic interval, then the number of substellar objects might rival or exceed the number of stars, representing an enormous reservoir of material that never reached the threshold for hydrogen burning. One of the most significant systematic checks on the stellar census comes from comparing the estimated stellar mass to the known total amount of ordinary matter in the universe. If the stellar census suggests a total stellar mass that exceeds the known matter budget, something is obviously wrong. Less obviously but equally importantly, if the stellar mass is much less than the matter budget, the question arises of where the rest of the matter is, and the answer to that question constrains what we think we know about the stellar census. Ordinary matter, the type made of protons, neutrons, and electrons as distinguished from dark matter, is called baryonic matter by physicists. The total density of baryonic matter in the universe is known precisely from two independent measurements that give consistent results: the abundances of helium and deuterium produced in Big Bang nucleosynthesis in the first few minutes after the Big Bang, and the acoustic oscillations visible in the cosmic microwave background. Both measurements give a baryon density corresponding to roughly 5% of the total energy density of the universe, with an uncertainty of a few percent. In a universe with a total energy density of the present value and the measured Hubble constant, the corresponding total baryonic mass within the observable universe is a specific and well-determined number. The question is where all these baryons are. Stars and gas visible in galaxies account for only a fraction of the expected baryons, the fraction corresponding to what can be seen in stars, cold gas, and hot intracluster gas in galaxy clusters. For many years, a substantial fraction of the expected baryons were missing, unaccounted for by any observed component. The leading explanation for the missing baryons, now confirmed by observations with several X-ray and ultraviolet space telescopes, is that they reside in a warm-hot intergalactic medium, a diffuse network of gas at temperatures between 100,000 and 10 million Kelvin that permeates the cosmic web between galaxy filaments. This gas is too hot to form stars and too diffuse to emit strongly at optical wavelengths, but it produces detectable absorption features in the spectra of background quasars and emission at X-ray wavelengths. The warm-hot intergalactic medium appears to account for the majority of the missing baryons and represents a reservoir of gas that has been processed through galaxies and expelled by supernovae and active galactic nuclei but not converted to stars. The implication for the stellar census is that star formation has been inefficient. Of all the baryonic matter in the universe, only a modest fraction has ever been incorporated into stars. Current estimates suggest that about 5 to 10% of all baryonic matter is currently in stars, with most of the rest in various forms of gas, some of it in galaxies as potential future stellar material and most of it in the intergalactic medium, too hot and diffuse to form stars on any relevant timescale. The stellar mass density of the universe is therefore a small fraction of the total matter budget, not because the census is missing most of the stars, but because most of the matter has never become a star. The fraction of baryons that have been processed through stars at some point in cosmic history is estimated from the metallicity of the universe. Because heavy elements are produced only in stellar interiors, the total abundance of heavy elements relative to hydrogen in the universe represents the fraction of material that has passed through at least one stellar generation. The mean metallicity of the universe, estimated from surveys of the intergalactic medium and from the integrated starlight of galaxies, suggests that roughly 10 to 15% of all baryons have been processed through stars and had their hydrogen converted to heavier elements at some point, with the fraction varying significantly between different environments. This processing fraction, combined with the baryon budget, provides another constraint on the total stellar census. If 10% of all baryons have been processed through stars, and the total baryon budget corresponds to a specific mass, then the total mass of material that has passed through stellar interiors at some point in history is 10% of that total, and this must be roughly consistent with the stellar census integrated over time, including the dead stars and their remnants. The consistency of this check is one of the reasons cosmologists are reasonably confident that the stellar mass density of the universe is in the right range even though the direct census carries large uncertainties. The warm-hot intergalactic medium that contains most of the missing baryons is particularly relevant to understanding galaxy evolution and the efficiency of star formation. The gas in this reservoir was not always there, it was expelled from galaxies through the energy input of supernovae and active galactic nuclei, which drive galactic winds and outflows that carry both gas and metals into the intergalactic medium. The total mass of gas expelled from galaxies is comparable to the total mass currently in stars, meaning that galaxies have expelled roughly as much gas as they have retained and converted to stars. The history of estimates of the number of stars in the universe is a story of continuous upward revision, with the magnitude of the estimate growing by many orders of magnitude over roughly 100 years. Understanding the history of this revision illuminates both how the current estimate was reached and how it might change in the future. The beginning of the modern era of galaxy astronomy can be dated to the 1920s, when Edwin Hubble used Cepheid variable stars to establish that the Andromeda Nebula was an independent galaxy rather than a nearby gas cloud within the Milky Way. Before Hubble's measurement, the universe was often implicitly identified with the Milky Way, and estimates of the number of stars were essentially estimates of the Milky Way's stellar content. Early estimates in this era placed the number of stars at a few billion, based on counts of stars visible with the telescopes of the day and simple models of how the apparent stellar density varied across the sky. After Hubble established the extragalactic nature of the spiral nebulae, estimates began to grow rapidly. If the Milky Way was one of many such systems, and if those systems were distributed throughout a universe of vast extent, the total stellar count would be multiplied by the number of galaxies. Early galaxy counts from photographic surveys suggested tens of millions of galaxies within the reach of the largest telescopes, which when combined with estimates of a few billion stars per galaxy gave total stellar counts of roughly 10 to the 18, a quintillion, in the 1930s and 1940s. The development of sensitive detectors and systematic galaxy surveys in the latter half of the 20th century pushed the estimated galaxy count to roughly 100 billion. Combined with improved estimates of stellar populations per galaxy, including the recognition that many galaxies have lower average stellar masses than the Milky Way, and incorporating the faint end of the stellar luminosity function, estimates settled in the range of 10 to the 22 to 10 to the 23 stars, roughly consistent with the current consensus. The 2016 upward revision of the galaxy count from roughly 100 billion to 2 trillion by Consolis and colleagues pushed the upper range of estimates toward 10 to the 24, though this revision has not been universally accepted and depends on modeling assumptions about early galaxy mergers rather than on direct detections of the earlier, smaller galaxies. The pattern that emerges from this history is consistent. Each time the reach of astronomical surveys has extended deeper, in distance, in wavelength, or in sensitivity, more objects have been found that the previous census missed. There is no compelling reason to believe that the current surveys have finally captured the complete picture. Future surveys, particularly those designed to detect the lowest mass stars and the faintest galaxies at the highest redshifts, will almost certainly find that the true census number is larger than current estimates, though by how much is genuinely unknown. The specific numbers associated with each era of stellar census are illuminating in detail. In 1920, the total number of stars in what astronomers called the universe, essentially the Milky Way, was estimated at roughly 1 billion by Harlow Shapley and others using star counts from photographic plates. By 1950, with the recognition that the Milky Way contained more stars than this and that the universe contained many galaxies, estimates had grown to roughly 10 to the 18. By 1970, systematic galaxy surveys and improved stellar population models pushed estimates to the range of 10 to the 20. By 1990, the estimate had settled around 10 to the 22. The current estimate of 10 to the 23 represents a factor of roughly 1,000 increase over the past 50 years. Examining why these increases happened reveals a consistent story. Each factor of 10 increase in the estimate was driven by the discovery of a previously unrecognized class of objects or a realization that previously counted classes had been severely undercounted. The discovery that the total galaxy population was 10 times larger than the deepest surveys detected contributed a factor of 10. The recognition that red dwarfs were more common than stellar population models based on brighter stars predicted contributed another factor. The realization that dust was obscuring large fractions of both the Milky Way and many distant galaxies contributed additional corrections. Whether the current estimate of 10 to the 23 is close to the true value or whether it too will be revised upward by a factor of 10 or more when future surveys reveal the next systematically missed population is unknown. The pattern of history suggests skepticism about any claim that the current census is nearly complete. What would give more confidence is the convergence of multiple independent methods, each with its own systematic uncertainties, toward the same number. Some degree of such convergence has occurred, with stellar population synthesis estimates, cosmic star formation history integrals, and extragalactic background light measurements all giving broadly consistent results. But the consistency is at the factor of several level, leaving substantial room for both upward and downward revision as methods improve. Having examined the components of the stellar census individually, the sources of uncertainty in each component, and the tools used to assemble them into an overall estimate, it is worth being precise about what the current best estimate actually says and what it does not say. The number most commonly quoted in scientific discussions and in reputable popular accounts of astronomy is approximately 10 to the 23rd stars in the observable universe, often expressed as 100 sextillion in long form. This number represents a reasonable central estimate derived from combining an estimate of roughly 100 billion galaxies, each containing on average roughly 1 trillion to 10 to the 11 solar masses of stars, converted to a number of individual stars using an assumed average stellar mass in the range of 0.3 to 0.5 solar masses. The resulting estimate is approximately 10 to the 22 to 10 to the 23 individual hydrogen-fusing stars. The range of plausible estimates spans from the lower end of about 10 to the 22, obtained by using conservative estimates of the galaxy count and mass-to-light ratios, to an upper end of roughly 10 to the 24, obtained by accepting the Consolus galaxy count of 2 trillion and using mass-to-light ratios appropriate for a mass function weighted toward low-mass stars, of the kind suggested by observations of massive elliptical galaxies. The central estimate and the upper and lower bounds therefore represent not a measurement uncertainty in the statistical sense but a systematic range determined by which assumptions and models are adopted for quantities that cannot be directly observed. Several specific observational uncertainties are the most important contributors to this range. The galaxy count uncertainty, already discussed, contributes a factor of up to 10. The uncertainty in the stellar mass-to-light ratio for different galaxy types contributes a factor of 2 to 3. The uncertainty in the initial mass function, particularly at the low mass end and in environments different from the solar neighborhood, contributes another factor of 2 to 3. The dust correction for highly obscured galaxies, particularly the contribution of starburst galaxies whose stellar content is largely hidden by dust, contributes perhaps another factor of 2. These sources of uncertainty are not independent, they can combine in either direction. An estimate that uses a high galaxy count, a bottom-heavy mass function, and generous dust corrections will give a number near the upper end of the range, perhaps 2 to 5 times 10 to the 23. An estimate that uses the conservative galaxy count, a mass function similar to what is observed locally, and standard dust corrections will give a number near the lower end, perhaps 3 to 5 times 10 to the 22. Neither extreme is clearly right based on currently available data, and the honest scientific answer to the question of how many stars there are spans the full range. The methodology used by different groups to arrive at their stellar census estimates reveals important differences in approach that contribute to the range of published numbers. Some groups begin from the galaxy luminosity function measured in surveys like the Sloan Digital Sky Survey and multiply by galaxy-type specific mass-to-light ratios and conversion factors from mass to number. Others begin from the cosmic star formation history and integrate the star formation rate over time, subtracting the mass returned to the interstellar medium by dying stars and adding appropriate fractions for different stellar remnant types. Still others use the extragalactic background light as a constraint and work backward from the total luminosity emitted by all stars to infer the total number. The remarkable feature of the stellar census problem is not that these different approaches give the same answer, because they do not, within a factor of several. It is that they give answers in the same general range, all within roughly a factor of 10 of each other, despite using completely different observational data and making largely independent assumptions about stellar populations and galaxy evolution. This rough convergence gives some confidence that the true number is within the range spanned by the estimates, even as the disagreement between specific estimates highlights the remaining uncertainties. The most important single piece of data that would most improve the stellar census is probably a more reliable measurement of the initial mass function at low masses in environments other than the solar neighborhood. If the bottom-heavy mass function suggested by some observations of elliptical galaxies were confirmed and its magnitude precisely determined, the total stellar count could increase by a factor of several. Alternatively, if better observations showed that the mass function in massive ellipticals is similar to the locally calibrated function, the upper end of the current estimate range would be disfavored and the central estimate would be better constrained. This measurement, more than any other single piece of information, would most reduce the uncertainty in the total stellar count. The number of stars in the observable universe is an input to one of the most interesting calculations in science, the estimation of how many places might support life, and it is worth spending time on what the stellar count implies for the question of life's abundance or rarity in the cosmos. The most famous framework for thinking about life in the universe is the Drake equation, formulated by Frank Drake in 1961 as a way of organizing the factors that determine how many communicating civilizations might exist in the Milky Way. The equation multiplies the star formation rate by the fraction of stars with planets, by the number of habitable planets per planetary system, by the fraction of habitable planets on which life originates, by the fraction of life-bearing worlds on which intelligence develops, by the fraction of intelligent species that develop detectable technology, and by the lifetime of a communicating civilization. Most of these factors are unknown to anywhere from 1 to 10 orders of magnitude. What the stellar census provides is not a resolution of the Drake equation's many uncertainties but a constraint on the denominator, the number of starting points from which life might emerge. With 100 sextillion stars in the observable universe, even extremely small fractions of that number produce large absolute numbers of potential life-bearing worlds. If only one star in a trillion has a planet on which life originates, that still gives 100 billion life-bearing worlds. If only one in a trillion of those produces intelligence, that gives 100 potentially technological civilizations in the observable universe. These numbers can be pushed up or down by orders of magnitude by adjusting the uncertain factors, but the enormous size of the stellar census makes it very difficult to argue that the absolute number of interesting worlds is truly small. The argument from numbers has limits that deserve acknowledgement. The fact that 100 sextillion starting points exist does not guarantee that any of them have produced life, because we do not know whether life's origin is an extremely common process, occurring whenever conditions are right, or an extremely rare one, requiring a combination of circumstances so improbable that it may have happened only once in the observable universe's history. The stellar census tells us the size of the lottery but not the winning odds. What the stellar census does unambiguously tell us is that the universe has had ample opportunity for chemistry, for planet formation, and for the long timescales that biological evolution requires. Among the 100 sextillion stars, the vast majority are long-lived red dwarfs that have been burning steadily for billions of years, many of them longer than the Sun has existed. The age distribution of stars in the universe includes billions that formed long before the Sun and that have had more time for any associated planets to develop whatever complexity the planetary conditions allow. The universe's age combined with its stellar population creates a landscape for life that is, in a purely physical sense, as rich as any serious model of cosmic habitability would require. The connection between the stellar census and the question of life also runs through the question of stellar stability. Red dwarf stars, while numerous, are energetically active in ways that may compromise their habitability. Young red dwarfs in particular produce powerful flares that emit intense ultraviolet and X-ray radiation, potentially stripping away planetary atmospheres and damaging surface-based life that lacks protection. Whether planets around red dwarfs can maintain atmospheres long enough for life to develop and persist is one of the most actively studied questions in astrobiology, with both theoretical arguments and observational data on both sides. The tidally locked orbits that planets in red dwarf habitable zones likely occupy, where one face of the planet always faces the star and the other is in permanent darkness, create additional environmental challenges that have no analog in the solar system. Whether life could persist in the permanently lit or permanently dark hemispheres, or in the narrow twilight zone between them, requires understanding atmospheric circulation patterns and photochemistry in conditions very different from Earth. If tidal locking severely restricts habitability, the effective number of habitable worlds among the abundant red dwarf systems would be much smaller than the raw planetary census suggests. The question of what fraction of stellar systems harbor complex multicellular life, intelligent life, or technological civilizations is even more uncertain than the stellar census itself. The number of stars provides an upper bound on the number of possible starting points for life, but the fraction of those starting points that produce any form of life, and the further fraction that produce the kind of complex organized biology that eventually leads to intelligence, are unknown by many orders of magnitude. The stellar count matters not because it resolves these questions but because it establishes the scale within which they must be answered. The answer to how many stars are in the universe is a number so large that it is almost impossible to hold in the mind as a quantity. 200 sextillion, or approximately 10 to the 23rd, is a number that exceeds by a factor of roughly 10,000 the total number of grains of sand on every beach and desert on Earth. It exceeds the number of all the atoms in a human body by a factor of trillions. It is larger than the number of seconds that have elapsed since the Big Bang by roughly 14 orders of magnitude. And yet the uncertainty in this number spans a factor of 10 or more, meaning we might be off by 100 sextillion in either direction and still be within the plausible range of what the current evidence supports. This combination of an almost incomprehensible absolute magnitude and a very substantial fractional uncertainty is not a failure of astronomy. It is what honestly confronting the problem looks like. The stellar census is not a tally made from direct observation of each individual object, the way you might count the chairs in a room or the words on a page. It is a statistical inference built from multiple layers of measurement and modeling, each layer introducing its own irreducible uncertainty, producing an estimate whose error bars honestly reflect the genuine limits of current knowledge. The history of the estimate is a history of upward revision. 100 years ago, the number of stars was estimated in the billions. 50 years ago, it was estimated in the quintillions. Today it is estimated in the sextillions. Each revision has been driven by new observational capabilities that revealed objects or populations the previous surveys missed. There is no compelling reason to think the current estimate is the final one. Future surveys with instruments yet to be built will almost certainly find more to count. What should endure from tonight's exploration is not any particular number but the structure of the problem, the understanding of where the estimate comes from, which parts of it are robust and which are fragile, how the estimate could change and in which direction the evidence suggests it might go. The stellar census is a living scientific question, not a settled answer, and the uncertainty in the number is itself one of its most scientifically interesting features, pointing directly at the observations and theoretical advances that will be most productive in the years ahead. The universe contains an almost uncountable number of stars, each one a sun, many of them potentially orbited by worlds, all of them products of the same physical processes of gravity and nuclear fusion that operate in the star 8 minutes light travel from the planet you are on. The count is imprecise. The wonder is not. The precision with which the stellar census can be performed depends on the precision of its most uncertain components, and the most uncertain component, the initial mass function in environments beyond the solar neighborhood, is genuinely hard to measure. It requires either resolving individual stars and galaxies far enough away to sample genuinely different environments, which is currently possible only for the most nearby galaxies, or inferring population properties from integrated light measurements that carry inherent degeneracies. Future extremely large ground-based telescopes, with primary mirrors 30 to 40 meters in diameter, will resolve individual stars at distances roughly 5 times greater than current facilities, extending direct mass function measurements into the environments of the Virgo cluster and other nearby overdense regions where elliptical galaxies are abundant. This extension will significantly constrain the most important remaining uncertainty in the stellar census. The James Webb Space Telescope's deep survey programs will continue to characterize the high redshift galaxy population, refining the galaxy count and the total stellar mass density at early epochs. The Nancy Grace Roman Space Telescope, with its large field of view and Hubble-quality angular resolution, will survey wide areas of sky in the near-infrared, detecting the red dwarf population in the Milky Way and nearby galaxies more completely than any previous survey. The combination of these facilities will provide a significantly improved stellar census within a decade. What the current stellar census tells us with confidence is that the universe is extraordinarily rich in stars, that this richness reflects a long history of matter assembling itself into stellar configuration under the influence of gravity and the conditions that quantum mechanics specifies for nuclear burning, and that the total number, whatever it turns out to be when measured with greater precision, is large enough that the universe has had ample opportunity to produce, through purely physical processes operating over billions of years across sextillions of starting points, whatever complexity the laws of physics permit. That is not a small thing to know.